Hello everyone, I am Lokender. In this talk, I will discuss my work on Pseudo RGB-D for self-improving monocular SLAM and depth prediction. Here is the outline of my talk. I will start with the motivation, then I will discuss the proposed self-improving framework. I will present qualitative and quantitative results. I will provide analysis of the self-improving framework. Finally, I conclude my talk. So let us start with the motivation. We know that traditional monocular RGB SLAM have well-known limitations in robustness and accuracy as compared to those leveraging active depth sensors like RGB-D SLAM. For example, we can see the RGB ORB-SLAM fails on sequence 1 of the KITTI odometry dataset, while RGB-D SLAM succeeds in the same sequence. An important point here to note is in order to run RGB-D SLAM, we need depth from active depth sensors like LiDAR. Question is, what if we do not have access to such an active depth sensor? Here comes the idea of using a pseudo depth sensor and run pseudo RGB-D SLAM, which I will present later. If we talk about the unsupervised CNN-based monocular depth prediction models, they formulate single image depth estimation as a novel view synthesis problem, with appearance-based photometric losses being central to their training strategy. Photometric losses largely rely on the brightness consistency assumption. Nearly all existing self-supervised approaches operate in a narrow baseline setting, optimizing the loss over a snippet of 2 to 5 consecutive frames. Consequently, for example, state-of-the-art models like MonoDep2, they generate inaccurate depth estimates for points that are farther away. As we can see in the top two rows, the depth estimates corresponding to Venn and sine pole are inaccurate. In the bottom row, the depth estimates of the close-by points are also not very accurate. Geometric monocular RGB SLAM and CNN-based monocular depth prediction represent two largely disjoint approaches towards building a 3D map of the surrounding environment. Both have their limitations. In this work, we demonstrate that the coupling of these two by leveraging the strengths of each mitigates the shortcomings of the other. Specifically, we propose a self-supervised, self-improving framework. In the following, I will first describe the overall working of the framework and then discuss the steps in detail. In this work, we have used MonoDep2 as our base unsupervised monocular depth prediction network. It consists of two subnetworks, depth network and pose network. We first pre-trained the MonoDep2 using monocular videos in a completely unsupervised manner. Inspired by the success of RGB-D SLAM, we postulate the use of an unsupervised CNN-based depth estimation model as a pseudo depth sensor. Once the depth network is trained, we prepare pseudo RGB-D data by combining the RGB and its depth estimated from the pre-trained CNN depth model and run RGB-D SLAM using pseudo RGB-D data. We call this a pseudo RGB-D SLAM. We use RGB-D version of ORB-SLAM 2 as our base RGB-D SLAM system. We save the SLAM outputs like camera poses, keyframes, 2D key points, and their depth values. We inject these output into the depth network to refine the depth predictions. Recall that MonoDep2 has two subnetworks, depth and pose network. For refinement purposes, we discard the pose network and use the SLAM output camera poses. We refine the depth network for one epoch. After the depth refinement, we regenerate pseudo RGB-D data and rerun the pseudo RGB-D SLAM for pose refinement. We iterate between improving poses and improving depths until we see no improvement in depth or poses. Next, I discuss the pose and depth refinement steps. Starting from the pose refinement, while it seems straightforward to use pseudo RGB-D data directly to run RGB-D SLAM, but it is not. This is because CNN predicts depth maps at very different scale compared to real active depth sensors like LiDAR. Therefore, we made some important adaptations. Instead of using a fixed baseline, we choose an adaptive baseline. For that, we make the setup of KITTI dataset and use the following relation to compute the adaptive baseline. Recall that we discard the pose network and use SLAM output camera poses. Now the question is why, and the answer is because SLAM poses are more accurate as compared to pose network of MonoDep2. As we can see in the figure, MonoDep2 camera trajectory drifted a lot. Additionally, during refinement, we use true camera intrinsics instead of average camera intrinsics. Next, I discuss the depth refinement step and the losses we use. We select 3 keyframes obtained from the pseudo RGB-D SLAM. Let chi be the set of key points visible in all the 3 keyframes. These are common tracked points obtained from SLAM. Di subscript C denote the depth of ith point in the central keyframe obtained from the depth network. IC-1 and IC+1 are the 2 temporally adjacent frames of the central keyframe. T subscript C2C-1 and C2C+1 denote the relative camera poses between central keyframe and its temporally adjacent frames. These relative poses are obtained from the SLAM. We use the network predicted depth and the SLAM output camera poses along with the known camera intrinsic matrix to synthesize the temporally adjacent frames. Let I prime be the corresponding synthesized frames. We can compute the photometric error PC between true and the synthesized adjacent frames. We also compute smoothness error. Since these losses involve only 3 consecutive frames, therefore we call them narrow baseline losses. We can back project all the visible key points to 3D and use the relative camera poses obtained from SLAM to transfer the back projected 3D point to the neighboring keyframes. We transfer the point from keyframe IC to IK1. We can compute the depth transfer loss as the L1 error between the transfer depth and the depth of the corresponding point in the keyframe K1 predicted by the depth network. Similarly, we can compute the depth transfer loss from K1 to C. By combining both of them, we get the symmetric depth transfer loss between keyframes K1 and C. Similarly, we can compute the symmetric depth transfer loss between the other two pairs, which are CK2 and K1K2. Since these losses involve temporally farther frames, they enforce the long-term wide baseline constraints. Therefore, we call them wide baseline losses. We have the depth estimate of the common tracked key points from both the depth network and the pseudo RGB-D SLAM. Therefore, we can compute depth consistency loss as the L1 error between the network predicted and SLAM estimated depth values. The total loss is the combination of both narrow and wide baseline losses. We evaluate our method on both depth prediction and pose estimation tasks. For depth experiment, we use standard KITTI eigen train test split. Our method outperform other monocular depth prediction approaches and several other methods that use stereo and stereo plus monocular training. If we look at the qualitative results, we can see the improvement in the depths. Especially, we can see the visual improvement in the depth of farther away points. We evaluate the pose refinement on KITTI autometry dataset. We use sequence 0 to 8 of KITTI autometry dataset for the self-improving loops and tested on sequence 9 and 10. We can see that the proposed method outperform in the self-supervised category in both RMSE and relative translation metrics. We also evaluated on full KITTI autometry test set sequences 11 to 21. We can see RGB ORB-SLAM failed in 3 sequences while pseudo RGB-D's initial failed in 2 sequences. And after using refined pseudo RGB-D data, it has failed only in 1 sequence. Qualitatively, we can see in sequence 9, although all the methods perform loop closure successfully, our methods generate camera trajectories that align better with the ground truth. In sequence 19, RGB SLAM failed after some time, while only our method succeeds. Next, we analyze the behavior of this self-improving framework. I have plotted the depth and pose evaluation metric with respect to self-improving loops. Depth metrics are computed at different max depth caps, ranging from 30 to 80 meters. In the subsequent self-improving loops, we can see the rate of reduction in the square relative and RMSE error is significant for farther away points compared to nearby points. For example, slope of error curves in figure B to C corresponding to max depth 80 is steeper than that of max depth 30. This validates our hypothesis of including wider baseline losses that help the depth network predict more accurate depth values for farther points. Overall, our joint narrow and wide baseline learning setup helps improve depth prediction of both nearby and farther away points and outperforms MonoDep 2. The error plots in figure D shows a decrease in pose error with self-improving loops and complement the improvement in depth evaluation metrics as shown in figure A to C. Coming to conclusion, we propose a self-improving framework to couple geometric and learning-based method for 3D perception. A win-win situation is achieved. Both the monocular SLAM and depth predictions are improved by a significant margin without any additional active depth sensor or ground truth level. Thank you.